Hi, Terry here for CS2300, our Computational Linear Algebra class. Today we're talking about applications. Today's applications lecture is about doing text and NLP processing using linear algebra. And this is based on material I've gotten from Bing Liu and Paula Matuka. So you start thinking about text, right, and databases and what we're trying to do with text. In the mid-90s, the data volume of unstructured text was larger than structured, but the structured market cap was much larger. But we were just beginning in the mid-90s to really understand how to deal much better with unstructured text. If we now look, Oracle now reports that about 90% of the world's data is held in unstructured formats, much larger than it was in the mid-90s, or it probably was that much in the 90s, we just didn't know how to get to it. And much less of it is numeric or structured coded data. So we're going to have to look at how do we get that data out. If we look at the growth, both structured and unstructured enterprise data is growing, but there's a whole lot more stuff that is growing, and about 80% of it is unstructured growth. So not only is it larger now, it's growing faster. So what is text processing? Well, text processing is really searching based on words or extracting data from documents based on words. And you all know lots of text documents in all kinds of formats, emails, corporate, web pages, reports, all kinds of stuff. There's just enough time and patience to read, but we still have those reports. We want to sort of gather information and find some nice way of doing it. So text mining is taking static documents and going through it. And traditionally, text mining uses structured data as an N by P matrix. So part of our goal is traditional data mining uses matrices. And text is not quite so structured. So we're going to want to talk today about how do we convert it into semi-structured data, where we're going to combine this into some form we can use. And in this case, we're going to actually turn everything that we talk about today into stuff we can do linear algebra over to solve some interesting questions. So if we think about search versus discovery, right? If I have structured data, then I can just do data retrieval, standard database type queries, or data mining. If I have unstructured text, I can do information retrieval, searching with unstructured data, and text mining. And we're going to spend our time on the these last two today. We're going to munge them together. So if I look at sort of text mining, our real goal is to gain knowledge from data stored as text. And as we said, that includes things like web pages, which is a big use of it, but also things like medical records, customer surveys, watching Twitter feeds, email filtering, incident reports. There's a lot of things we want to do using data, and we can do it both interactively for search or text mining, which is generally viewed as less interactive, where we're processing lots of documents. Generally, it falls into two categories: retrieval, which is what related to search, which is there's some large amount of data out there, and we want to find the closest or some number of close items in the specified query. You're all used to this. This is what you do when you use Google every day. We've talked about Google's eigenvector, which is part of how it does page ranks, but we haven't talked about how you actually do the searching parts of finding what's matter, and that's a little bit what we're going to cover today. And then there's also the analysis of text, where you go through it, and then you produce reports and do things like document classification. I'll talk about at the very end of today's lecture some of the work I did on document classification using techniques. So for retrieval, we want to find the top K objects out of hundreds, thousands, millions that are similar to your query. Your program 5 is actually very related to this, so this is sort of an introduction to that concept of an idea. You can view this as interactive data mining, where the query is not specified a priori. In your program assignment, you actually get the queries the day or so before you have to run everything. The main problems of text retrieval, though, are really threefold. The first, what does it mean to find the similar documents? If you've all done searches, you know that sometimes some of the things they find don't seem relevant, others seem very relevant. So we have to have some good idea of what similar means. At a different level, more difficult, which we're not going to touch, how do we know if you have the right documents? So there's a whole bunch of analysis to figure out. I returned stuff, but you don't know if you did a web search, did you miss things that were relevant? That's a little bit more difficult. And then how can you incorporate user feedback? Both of these are really important problems in overall information retrieval and text retrieval. We're not going to talk about them today, but I just sort of point out those are there. We're going to start with and look today only at the meaning of similar, because that's what your program is. I'm just going to look at. So when we look at text mining analysis, we want to figure out what words are present. So we're now analyzing a bunch of documents. What words or documents are surprising, which words can help define the document, what are interesting text or phrases. In some of the work I've done where we tried to figure out by analyzing the document, should this document have been classified at the secret level, at the confidential level, or should it be unclassified? We're just trying to do some very simple analysis based on all those things to figure out security levels of the documents. For text retrieval, some of the challenges, calculating similarity is really not that obvious. I already mentioned this, right? So what's the distance between two sentences or two queries? Evaluating it is hard. There is no right or wrong answer. We're not going to worry about evaluating it, but there is some ground truth you can do in the real research field. We're just not going to do that here. In my stuff on, for example, security classification or retrieval, because we looked at it from both ways, we actually knew the classification because WikiLeaks had classified all the documents. Right? They came with classifications when they were released. They didn't classify them; they came that way when they were leaked. But not all data sets have those kinds of answers. Users can query things that they've never seen before. You can have misspellings, foreign terms, new terms. All of those are difficult, but we'll talk about how you might get those in here. So your goal is really some sort of scoring function that is a little bit different than what we talked about for classification last week when we tried to say which side of the plane is it on. We really want to find out what's close, and we need to figure out a definition of close that gets us close to what users are interested in. And then text makes this, all these functions, by the way, are true for all of retrieval. If I'm with image retrieval, how similar images are difficult. So text has a secondary problem, which is it can words can actually hide some of their semantic content. So we have this idea of synonymy, where a word doesn't really appear anywhere in the document, even though the document is very closely related. So it has synonyms, not the real words, and polysemy, where the word may have different meanings in different contexts. For the word for example, word mining and data mining has both physical mining and data mining contexts, and now Bitcoin mining. So there's lots of different things can mean the same thing. So we're going to look at this from a very simple way. We're going to look at what is called a bag of words, or BAO, representation, meaning that it's really just carried by the vocabulary. We're going to ignore the syntax. So we're not doing full natural language because we're not worrying about grammar and syntax. We're just worrying about these are the words that show up. And we're hoping that by doing some domain modeling, we can capture some detailed meaning about the knowledge in that context. An intermediate position is to look at vocabulary words grouped together, things what are called n-grams. We're not going to look at that, but they're a way of putting some spatial locality to it. And most search engines, for example, do actually use order and locations a little bit. These still lead to statistical approaches, but they can have richer representations in a single term, but they're a lot more complicated. So for your assignment, you can do something very simple. So let's think about what we would like this to look like. Let's say we were looking for articles about the golfer Tiger Woods, and an API Newswire brings up stories about the golfer, followed by articles about golf tournaments that don't even mention his name. And I'm sure you've all had some examples of searches where you put in a word and it brings up documents that don't have that word. You get a little annoyed. In fact, if you're in Google and you want to make sure the word has to appear, you have to put it in quotes. Otherwise, it won't necessarily appear. So constraining your search to days when no articles were about Tiger Woods, you'll still bring up stories about golf tournaments and well-known players. Nothing about Tiger Woods, or they said don't necessarily talk about Tiger Woods. So in a sense, we as a people understand that if I ask about Tiger Woods, I might be interested in general golf. And golf might be there even though his name Tiger Woods didn't show up. Maybe they just refer to him as Tiger, or they refer to him as TW, or there's a photo of him and you can't tell who he is, but you know who he is because you know about golf. There's lots of reasons why you would like things that use semantics. So if we hear some examples of phrases, I'm not going to read through them all. You can read them on the screen. But if we took these, now what we're going to do is we're going to convert these to a matrix. And this first simple version of a matrix is a sort of binary representation. So across the top of our matrix, we have all the major words that show up. We're going to get rid of or stop words like at and the. We're not going to use them because they're too small. Even the word second is way too common. But we'll have all the words Tiger Woods, drama cut, steak, opening. These are all relatively less common words we're going to put up in there. And then, although I didn't put it here on the side, these should have been the first 1, 2, 3, 4, showing which sentences had which words. And so those 4 words then each one becomes a row in our matrix. And now you can see how we've turned words into a matrix. Right now we have zeros and ones, where each row is a sentence or a document. If we want to think of the broader sense, it's a document. And each column is one of the words we're going to have that we put together. And now you'll also notice, if we go back and look at this, that the words tiger shows up with funai frequently. And so when this last document talks about funai, we might think it still has something to do with related to woods, and so on. There's lots of relationships that are mentioned. And so by creating this term document matrix and examining it, we can find potential relationships which are called latent or hidden. They're tied together by meaning or semantics of the term. So tiger and woods have a semantic meaning together, but so does tiger and champion and funai, right? That's a latent meaning. Tiger Woods is, it's his name, that makes sense. But that he keeps showing up with funai is a little different, so it's a little latent, a little harder to see. And this leads us to this idea of latent semantic indexing and latent semantic analysis we're going to talk about. The problem is if we actually did all the words in a document times all the documents, the dimensionality is really high. And if we take each term of the matrix by the number of documents, it's ridiculously large. We need some way to trim away useful, to trim down to things that are just useful. So the first is to throw away anything that's not useful. We have this idea of stop words, words that you just ignore because they don't really matter. And then we're going to try and identify clusters and pick representative terms, and that's what we're going to spend more of our time on. So what do we throw away? Well, we throw away things that are prepositions, nouns, articles, conjunctions, that are really not the most important words. We also get rid of very frequent words that don't add to the domain semantic. So words that occur all the time, like big, good, bad, very, they appear in so many documents they're just not worth it. And then oddly enough, we also throw away, or can throw away, very infrequent words that, for example, are people's names. We have to be careful, so we have to figure out how often they show up in documents. So when we get done, we'll have a condensed matrix that we can assume are the most useful terms. It's still very large, it's still very sparse, but it's a basic index table for what we're going to do. So now we've talked about how we're going to identify clusters and pick the representative terms, find out what are the contexts. So latent semantic indexing is the application of what we're going to use SVD to get there, to image retrieval, and latent semantic analysis is the more general term used to its broader application in lots of ways. The features start as words, we turn them into numbers, and examples are text passages or documents or whatever. This idea is used in lots of places for grading, so it's not just quite indexing, that's where it becomes analysis, for automated analysis of documents to put them in groups and whatever. And we get the latent semantic from latent, not visible on the surface, and semantic meaning the meanings that come together. So now we're going to go through a little bit more involved examples so you can sort of see how this works. So now I'm not going to show you the whole words, we're just going to show you 10 documents in 6 terms. So here are our 10 documents. Here are our 6 terms: database, SQL, index, regression, likelihood, and linear. We put all these together. And this document sort of says how often each of these documents have each of these words. So document 1 has a lot of references to databases, SQL, index, and nothing about regression, likelihood, but a little bit about linear. Whereas document 10 has a little bit about databases and a lot of regression, likelihood, and a lot of linear. So each document now becomes a vector. In this case, we're doing full counts. You could also do this with just Boolean. It's just not as generally as effective if you only do Boolean. So now our query, if we want to do a search, becomes something like a list of words that we convert into a matrix. So if we had that term document matrix we just saw, and somebody searched for the word database index, we go back and look. The word database is one of our words. The word index is not, so we threw that word out. Index is one of our words. It's the second one. So we get our representation of the search is 101000, right? That's a simple translation. We have a dictionary that looks up each word, decides if it's in our terms. If it is, it becomes part of our search. And now our goal is to find this vector or something related to this vector in the database. So one way of doing that, which we'll come back to, is what's called cosine distance between the term document and the term document and the frequency diagram. That returns a ranked vector documents. That's called vector-based processing. We'll come back to that, but we'll show you a slightly better approach now, which is based on latent semantic indexing. So if we just do basic word searches, like find every document that has those words, we don't necessarily find out documents that don't have them, and we don't necessarily get a very good weighting over how related they are. So we really want this semantics to be as powerful as we can. We want the system to deal with synonyms and anything else. And if I try and do that manually by saying, okay, what are all the synonyms for a database? Well, is SQL a synonym? Well, it's not quite, because there are databases that are not, right? So you get this whole very difficult thing of trying to figure out how to deal with things that are related but are not exactly synonyms. And so the goal of LSI is to actually extract that hidden meaning in the documents and really search what you meant, not what you said. And we're going to get what you meant from the way things are related in documents. So we're going to come back to this using, our singular value decomposition. We're going to have our term space, which might be thousands of dimensions for a real project. Your assignment, you'll only be allowed to have 50. And then we'll have a document space, and we want to project or map those together. So the idea is to end up with much smaller dimensions, and I forgot to check if this link's still valid. I'll follow it, you'll see it good. So you want to have this, we have much smaller dimensions, and you're going to reduce the dimensionality of the document. This is related to what we call PCA, but it's done slightly differently. So we're going to start off with n words by m documents, and we're going to find the least squares best n by k matrix, where the rows of m map input features to encoded feature clusters, and the columns of the eigenvector, or of the singular vector, are going to actually tell us the things that are in the constant. It's very related to eigendecomposition, factor analysis, principal component analysis. And SVD is a subroutine in many math packages. For your assignment, you're going to be allowed to pull in those if you want them. So we're going to try and approximate this by using the first k principal component directions provided by the best set of k orthogonal basis vectors from SVD. And the idea is that these explain the most variance in the data. And if they explain the most variance, they're actually coupling together the semantics of related things. Each direction here is linear combination of topics and define sort of clustering of topics in the data. So we take our term matrix, term document matrix, we're going to do the SVD, and in this case we're going to get, we started off with something that was 10 by 6. Our term document will be 10 by 6, our eigenvalue matrix, and then our basis for the null space and the row space. So for our example, the ones I just showed you, the matrix showed earlier, you actually get a set of singular values. You'll see the first one's 77, 69, 22, 13, 12, and 4. The first couple are very big, and then they drop off very fast. And in fact, the fractional variance explained by just the first two principal components is 92%. So 92% of the information is carried in two principal components. We don't really get that much out of the rest. If I were to look at those two principal components, I can think of them as coefficients of, as vectors, but now I can take every document and I can multiply them by those vectors and I get a coefficient, a weight. Each of those weights then can be viewed as a position in 2D space, right? Because they're just now two-dimensional coefficients. And if I plot all of the documents in that 2D space, we'll see there's a little cluster of some things over here, and then there's another of some cluster of things over here. And the first two principal components emphasizes the first two terms, right? This term and then that term, we put them together. And it really separates the two clusters. We can easily see there's a bunch of documents here and a bunch of documents here. And we can now do clustering or separation in this space instead of the original space. And just to make it interesting, if we put just one-word documents, SQL and databases, with each of those words in there many times, and then pass it through the system, you'd actually end up with the word SQL over here and the word database over here. They're very close in this space. They're very high in this first PC1 dimension. Even though neither of these terms are actually in the other one's documents, these might still be the closest documents related to searches. So they're very close. A second model, so before I go on, so your homework assignment for program 3 is actually to implement program 5, is to implement some LSI-based approaches and find some small number of dimensions. You're going to keep, I think, 50, and then work on that. There are other document models used. So another very common model is what's called vector space model. In the vector space model, documents are also treated as bag of words. Each document is represented as a vector. However, the term weights are no longer 0 or 1. We turn them into a weighted scheme, which I'll show you in a second. The most two common are weighted frequency schemes and normalized by frequency. So I can take the term weighting scheme where I take the frequency divided by the word that occurred the most. I can also do one what's called inverse document frequency, where I take the number of documents and divide by the number of documents that the term TI shows up in, and we can use that as a weighting. And then the final term IDF, so this is the term frequency inverse document frequency, which is a very common weighting function, really takes the term frequency times the document frequency. None of these, notice, are actually looking at the number of words in a document. They're actually, this one implicitly has a little bit because they're looking at how frequently does every word show up, but not the total number of words. And this is because we don't really want to give advantages to documents that are much larger or much smaller. We're talking about the semantic content of them. So if I want to retrieve something in this vector space model, we represent the query in a very similar way. We're going to take the document, convert it to a vector, and then we're going to take, say, the cosine or Euclidean distance between them, which you can sort of see from a linear algebra point of view. We're just going to take the dot product divided by the norms of each of the two vectors. So again, we're turning all of our things into linear algebra objects that we can work on. And this cosine is also commonly used in the clustering. We could also do some other kinds of distance metrics. So now that we have that document, we could be looking at it in terms of Euclidean distance, cosine distance, and we'll look at it in a second. So coming back just to refresh it so you can sort of see it, because we're going to see some representation of a second. Here's the distances we had. So what would you expect the distances to look like? Well, you might notice that there's a lot of large numbers here and small numbers here, large numbers here and small numbers here. So when we look at them in terms of Euclidean distance, you'll sort of see there's a very small distance to each of these sort of blocks, and these two bigger blocks have much larger values. But when I look at them in the cosine space, there's a much greater separation, and everything in this column is smaller than, even though these other things are in the same block, they're much larger. If we go back and look for a second, right? This column is generally much smaller than this column, even though they're both large, right? Things over here are much smaller and over. So when we come back to our term document structure, right, we have to be a little careful in what words we put in the list. Not all words are equal. Words that are the same should be treated the same. So we're going to really quickly talk about two things: stop words and stemming. So stop words, these are the things I already mentioned. These are the words that really they don't have any information. For ancient historical reasons, they are called stop words. I think it'd be better if you just think of them as drop words, because they're the words you just drop. You see them and you forget them. It doesn't matter if they say the, of, and has some interesting meanings from a query point of view, but it's going to be dropped. Generally, there's between 400 and 500 such words. I think I'll give you a list of a couple hundred to ignore. For applications with a specific domain, they might have very specialized words. First, we do this to reduce the size of the indexing file. Stop words account for 20 to 30% of the total words. It not only improves efficiency in terms of speed and space, but it actually turns out to actually have a lot of improvement in the actual matching accuracy. Stop words have a lot of things in common, and you don't want to pull up a bunch of documents that have lots of uses of the same prepositional phrases, but don't actually have any content in common. Stemming is another important part. You're encouraged, but not required, to do this in your program 5. We're going to look at techniques to find the root stem of a word, and you can just find libraries to do this. But all of the words user, users, used, using, all of these are highly related. Engineering, engineered, engineer. The stem of each of those is use and engineer. You'll notice that users and used are not exactly the same, but they're all related to this concept of use in one way or another. So stemming improves the efficiency, because again, you get to reduce the number of words, often by as much as 40 to 50%, and you don't have to try and infer the relationship between engineer and engineered, or engineering, right? Because if you don't have enough documents, that may be harder for you to find. So common word stemming methods are to remove words that end in an S, drop the S. If it ends in ES, drop the S. If the word ends in ING, delete the ING. And so on. There's a whole bunch of these. The idea of stemming algorithms and whatever, you might see again if you take another class in AI or machine learning or natural language. Or it actually is also related to some grammars. There's grammars you can do this. Not critical for this class, but I wanted you to understand the concept because it affects how you use search engines. And when you go to use some of these tools, you might see a library for doing word stemming. Now you know what it means. Some of the other things we can do, but we're not going to get into for this class, are with this kind of representation, are sort of automated document classification. So we might want to have a lot of online documents. We want to classify them. So we might want to classify emails into spam and ham. We might want to classify documents into classified and not, customer requests into complaints, inquiries, insults, whatever. Anything you have as a bunch of text, you might want to classify in different categories for its processing. So as a classification problem, we basically have a training set where humans have labeled them somehow, and then we, like we did for the lines, we come up with a system that discovers classification rules. Now that you've seen how to turn documents into matrices, you could already apply the simple multi-layer perceptron you had from last class. Once you've turned them into matrices, you can play the same kinds of game, because now you have numeric entries going into a network to play some games. There's lots of other techniques like the regression, naive Bayes, linear discriminant analysis. There's not tree techniques and forests are not quite as good because of the way documents interact. I've done a little bit of work in this space doing, as I said, big security analysis for documents, where we've gotten a couple of award-winning papers. Gerald, the CS department chair here, this is his primary research area. So if you're interested in this, there's opportunities for you to explore this as sort of a research question. So clustering is related, but not quite the same as classifying, because you can do clustering or sort of unsupervised learning of documents that sort of groups them together. It requires no real training or predetermined taxonomies. You sort of do some pre-processing to get the words together, put them in a numeric form, cluster them into using some clustering technique like spectral clustering, which I'll talk about in another applications video, and then sort of slicing them back out into pieces. Like all clustering examples, the success of this is sort of relative depending on your problem, what you mean by clustering, how you get your document frequencies. There's a whole bunch of things that will go on, but clustering is something that can actually be used to improve classification, which we did in one of our papers. So hopefully this short applications video has given you an idea how you can do linear algebra to improve unstructured document analysis by turning documents into matrices and then doing things like singular value decomposition or vector math to combine them.